Hello, everyone. I'm Bikram. Today, I will be presenting this adversarial attacks on time series. In this paper, uh, basically talks about time series classification models, which have been garnering significant importance in the research community. However, we find that not much research has been done on generating adversarial samples for these models. These adversarial samples, they can quickly become a security concern. This topic, it deals with adversarial attacks in time series data. As with time series data, network packets, they are also similar and they arrive in a timely fashion. And network packets are also susceptible to attacks from foreign elements like hackers. So while we talk about time series data, it's important to remember that these kind of attacks can not only happen with just time series data, but it can happen with other kinds of data also. So let's first look at the challenges what I faced. I will show in a minute. I'll show you in code basically what the challenges were when I started running the code. The first and foremost and major challenge which I faced was the TensorFlow version. So this code, which was almost 5-6 years ago, it was written with TensorFlow version 1, whereas that TensorFlow version is not even available at this moment. So currently, the latest TensorFlow version is 2.15, 0.6, 0.5, something like that. So many of the functionalities which were written, I had to change those. I had to modify and get updated with the new TensorFlow versions. So that was one of the major challenges which I faced when trying to run the base code. The second thing was understanding the metrics. This adversarial attacks on time series, they have various metrics. And to understand that, it took a lot of digging into a lot of functions to understand those specific metrics, to understand what the results meant. The third one was understanding the overall code structure. Since this project requires improving or changing on the existing code base, so it's imperative to understand where each code is coming from and where can we make the changes which can create a significant impact. And then another thing which I overlooked was the running time. So basically, when running this model, it takes a significant amount of time to train the model, and that initially I hadn't taken into consideration. So these were some of the challenges which I faced while trying to run the code. So now let's look at the code demo. So as you can see in my screen, so this is basically the folder structure which I got from GitHub. And basically this file, the search tsnn gatn whitebox.py, in this paper, they discuss about by GATN, it is gradient adversarial transformation network, which is used to transform a time series data and create adversarial samples on that time series data. So these search ones, I worked on white box attacks, and these search ones, the search TSNN white box attack is the one file which is used to train. And after training, you can run the eval, which is used to test, as well as you can run the visualizer to and give individual samples to visualize what the time series data and what the adversarial samples they look like. So first, what we have to run is this search tsnn whitebox.py. In this whitebox.py, if you run this, let me run it. If you run this, while you can test on multiple data, I have selected only one data set for demonstration, which will help with because we have a limited time in this demonstration. So what will happen is in the logs files, this one. So, yes. So in the log file, these are the previous runs. And in the log files, you can see that for generate dataset 21, you get the results. And this result is generated on a CNN-based model. So first we have our based time series network. And what we do is we use the gradient adversarial transformation network to generate adversarial samples. And then we feed those adversarial samples and we basically classify those adversarial samples to using a CNN-based classification model, which is defined here in utils. Sorry, in models. In models, a fully convolutional network, which is accessed through here, if you can see, the classifier model is a fully convolutional network model. And what happens in this results is this is tested for various beta, and the train MSC is the mean squared error between the adversarial sample and the actual data. And this train accuracy realistic, it's basically the accuracy between the y predicted of the true values as well as the y of the y predicted of the adversarial when you run the adversarial sample through the classifier model. And the accuracy optimistic is the one when you have the when you run that data set, when you run the original data set through the classifier, you get a predicted y. So comparing the predicted y as well as the adversarial y's, you get the y optimistic. So as you can see, the y optimistic is very high, which means that the adversarial samples, they are able to fool the time series and fool the classifier because it's very close when you're running the predicted ones from the classifier model as well as the adversarial ones. So since it's very close, which means that it is 100%, like and the target rate is refers to the rate or proportion of instances where the model's predictions are classified as the target class among the instances that were originally not the target class according to the ground truth levels. So as you can see that 100% of the adversarial samples, they were able to fool the classifier network for the CNN model. So what improvement did I make? What I did is the researchers, they had tested this white box model only for a convolutional neural network. So what I did is instead of just testing for convolutional neural network, I tested it for LSTM network as well. So I wrote my LSTM network where I defined two LSTM layers. Here you can define multiple LSTM layers, but as I've observed that the LSTM model, it takes a lot of time to run. So I have only taken two layers for saving time consumption as well as reducing the number of units. And this, for the LSTM file, it can be run from the white box new file. So if you see, it's running for just 10 epochs, but while training, this is a secondary train, but because this has already been trained initially. If you can see here, that during initial train, it requires 300 epochs to train it properly. Then it saves the weights. And while you train it again, it saves those weights, and it can train only for 10 epochs. Otherwise, the model is really, really slow for at least for the LSTM network. So once it's run, we can see the log files of the LSTM as well. We can see the log files for the LSTM as well. And you can see for LSTM, the number of adversaries which got through, it was way more. So for some reason, the MSC is not coming for the LSTM network. That's an issue with the dataset, not with the LSTM network. So the number of adversaries for at least for that data set, the data set number 21 is way more. So this LSTM network, it was so for the LSTM network, the number of adversaries that were found is way higher. So what happens here is that it's difficult to fool the LSTM network rather than the CNN network, where the number of LSTM is 21. Yeah, the number of adversaries that were found was almost nil. So we found that for LSTM, when we compare that, in this case, for this data set, it was very difficult to fool the LSTM network, as it found the adversaries instead of the CNN one, where the adversaries got through. So with this, we can run the evaluations also, where this is still running. Those results are from the previous ones. We can run the evaluation and we find this data, and we can run the evaluation on the new one, white box. And we find for the LSTM ones, it is more for the testing phase, it is also more likely to find the adversaries. Coming to visualization, this is interesting, where we can visualize a sample for a particular data set. So if we visualize one sample, this is a sample for the LSTM network, where in images, here 7 seconds ago, you can see the adversarial samples that it didn't come through because it didn't fit in this range. And if you run for the CNN model, you can see the sample. So thank you. That was basically my demonstration. You can ask any questions now. Thank you.